This video is a basic introduction to trig functions, the relationships between them, and the graphs of these functions. The two most commonly known trig functions are the sine and cosine functions. I just want to walk through some general properties of these graphs. So for both sine and cosine, our amplitude is 1, our period is 2 pi, our midline is at 0, the domain is from negative infinity to positive infinity, and the range is from negative 1 to positive 1. Regarding the graphs specifically, our cosine function has a y-intercept at its maximum value, and as x increases, our cosine function decreases, so it kind of drops down from that peak. And then our sine function has a y-intercept there on the midline, at the middle of the function, and increases before then decreasing. Now, the sine and cosine functions are very, very similar. As you can see, it looks like one is just a little bit kind of off-center from the other. So, this distance here, how much off they are is one way to think about it, is pi over 2. So that means if I were to take my cosine function and shift the entire thing, pi over 2, to the right, I would get my sine function. Similarly, if I start with my sine function and I take it and I shift it pi over 2 to the left, I would end up with my cosine function. So I just want to refer back to our general formula for transformations here. Our horizontal shift, is our h. So x minus h means that we move to the right by h, and then x plus h means that we're going to move to the left by h. So using my knowledge of the sine and cosine functions and of transformations, I can write down two identities that I know are always going to be true. The first identity that I want to draw your attention to is cosine of theta minus 2 pi equals sine theta. So this minus pi over 2, not 2 pi, this pi over 2 here on the inside means that we shift our cosine function to the right by pi over 2, and we can see from our graph that if we do that, we shift our cosine function to the right by pi over 2, we get our sine function. Similarly, we can write sine of theta plus pi over 2 equals cosine of theta, because if we take our sine function and shift it to the left by pi over 2, we get our cosine function. Now, I just want to talk about how these two identities make sense in terms of the unit circle. So if we start with our angle theta, and we increase our theta by pi over 2, we can think of that as rotating our unit circle in the positive direction, pi over 2. So when we do this, all of our x's and y's kind of switch places. So the same happens if we go in the other direction, by pi over 2. So our horizontal distances now become our cosines, are what used to be our sines, and then what used to be our cosines are now our vertical distances, our sines. And we achieve this by rotating one direction or another by 90 degrees, which is the same as adding or subtracting pi over 2 to our angles. So it's pretty consistent what's going on here. And I want you to just kind of latch onto and remember whichever way helps you make sense of it the most. So here in the top left, I have sketched the graph of the sine function. So we kind of talked about some of the other properties of the sine function. Now I want to talk about its symmetry. The symmetry of the sine function is about the origin. So this tells us two things. The first being that sine is an odd function. And to be an odd function, that means that negative f of x equals f of negative x. Or you could think of it in terms of points. So for every xy, there must also be a negative x, negative y on the graph of your function. So from this information, we can write that sine of negative theta equals negative sine of theta. We know this is true based solely on the graph of the sine function, but I think it might be helpful to also look at it in terms of the unit circle. So just really quickly, I want to draw in some arbitrary angle theta, and also its counterpart negative theta, just so we can kind of compare what's going on. So our sine of theta is some positive y value. And then the sine of negative theta is the same, except it's a negative version. So it makes sense that if we change the sign of our theta, so we're going in the negative direction instead of the positive direction, that it's also going to change the value of our sine, because our SIGN is different depending on which direction we go. So you can think about the oddness of sine either in terms of what's happening with the values on the unit circle or on the graph of sine itself. So just remember that symmetry about the origin, O, means that your function is odd, O. Now I want to take a look at the symmetry of the cosine function. So as you can see, the cosine function has symmetry about the y-axis. This means that it is an even function. So another really common even function is x squared, and it's got the even exponent, so that's a good way to remember it. And then also for our odd function, x cubed has an odd exponent, and it has an odd symmetry, a symmetry about the origin. So that's another way to help you keep straight what's going on. So algebraically, in order for a function to be even, we have to have f of negative x equals f of x. So changing the sign of our input doesn't matter. So we can see that whether we go negative pi over 2 or positive pi over 2, our output is still 0. Thus we have cosine of negative theta equals cosine of theta. And in terms of points, we can think of for every xy, we have to have a negative xy. Just like we did with the sine function, I also want to look at the symmetry of the cosine function in terms of the unit circles to kind of see how it makes sense that it's going to be an even function. So here I've drawn in my positive theta, and here is my negative theta. Now my cosine is my x coordinate. So whether I'm looking at the positive or the negative, my x-coordinate is the same. So remember, our cosine is our x-coordinate, so if our x-coordinate is the same, regardless of whether our theta is going in the negative direction or the positive direction. Now I'm going to consider my unit circle one more time. So let's say I have an angle, theta, and this angle has a height, sine of x, and a base, cosine, or of theta, I guess, sorry, not x. Since I'm looking at the unit circle, I know that my hypotenuse here has a value of 1. So by the Pythagorean theorem, I have that sine squared of theta plus cosine squared of theta equals 1. So this is literally just plugging into the Pythagorean theorem. But the cool thing about it is that our sine and cosine aren't dependent on what our radius is. It's only dependent on the angle. So regardless of what kind of circle you're looking at, or if it's a triangle, this relationship is always going to be true. So sine squared of theta plus cosine squared of theta equals 1. The next thing that I'm going to introduce you to are the other trig functions, so tangent, cotangent, secant, and cosecant. However, before I do that, I want to talk about limits a little bit, and that will help us construct the graphs of these other trig functions. So, in general, you can think of a limit as being the number that your outputs approach as the inputs approach some given number. So my AP Calculus teacher liked to call it gets close to math. So as x gets close to a particular number, what number does y get close to? So just a really basic example, if we look at the line y equals x, as y gets really close to 0, our x also gets close to 0. Or as our x gets close to positive infinity, our y also gets close to positive infinity. Or we could even go the other direction and say as x gets close to negative infinity, our y also gets close to negative infinity, which of course you can also visualize on the graph. So as our x's get bigger, our y's get bigger. As our x's get smaller, our y's get smaller. This is just the very basic idea of what it means to be a limit. In particular, I'm concerned about what happens to y equals 1 over x in two different scenarios. So one scenario being as x goes off to infinity, either positive or negative, and then what happens as x gets close to 0. Now, we can't plug in 0 for x, because then we'd be dividing by 0, and that's bad news. But we also can't plug in either positive or negative infinity for x, because positive and negative infinity are not numbers, they're just ideas. So we have to kind of look at the graph to determine what's happening as x gets really, really big or really, really small, or as x approaches 0. So 1 over x is called a rational function. The graph of the rational function is a hyperbola, as I've drawn in here, with asymptotes at x equals 0 and y equals 0. So an asymptote means our graph gets close to it, but it doesn't ever actually touch it. So the first thing I want to know is what happens as x goes to positive infinity. So positive infinity is going to be way over here. So as my x goes this direction, I'm going to use a different color. So as my x gets closer and closer to positive infinity, we can see that our outputs here get closer and closer to 0. So as x approaches positive infinity, y approaches 0. Similarly, if we look at our x's as x approaches negative infinity, our y's approach 0. They get really, really close to 0, but they don't ever quite reach it. And then as my x approaches 0, it kind of depends on which direction I'm coming from, right, on what happens. So if I come in from the left, my y's are going down, 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 and they're getting really, really negative. So as I come in to 0 from the negative direction, my y approaches negative infinity. However, if my x comes into 0 from the positive direction, like this, my outputs go off to positive infinity. So you just kind of look at the general trend of a graph, and then that's kind of what a limit tells us. So these two facts are going to be really, really helpful when we construct the graphs of our other trig functions. The first new trig function that I want to talk about is the tangent function, tangent of theta, and that is defined to be sine of theta over cosine of theta. So this means that the tangent of our function depends on what's going on with our sine and our cosine. As we construct our graph, I just went ahead and popped up a unit circle so we can use it to quickly refer to. I told you at the beginning that the key points we would use for graphing our trig functions are the quadrantal angles. So that is going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. So these are the angles that we really care about seeing what happens to on our graph. So I'm going to make sure that I have those labeled clearly on my axis, my x-axis. So the first thing that I want to notice is that my tangent we can think of as a fraction. And I know that a fraction equals 0 anytime the numerator equals 0. Therefore, anytime my sine here is 0, then my tangent is automatically going to be 0 as well. So I can go to my unit circle briefly and just kind of notice my y-coordinate is 0 here at pi over 2 and at pi. So that's also where my tangent function is going to be 0. So it was at pi over 2 and at pi is where my sine is 0. Another really useful property about fractions that I can apply is that my tangent function is automatically going to be undefined any place that my cosine is 0 because I'm not allowed to divide by 0. Therefore, I'm not going to have any values where my cosine is 0, so those are going to be vertical asymptotes. I can see from my unit circle that my cosine equals 0 at pi over 2 and at 3 pi over 2. So those are going to be my asymptotes. Now to fill out the general shape of my graph, I'm going to refer to the unit circle once again. I still need to figure out what's going on at 0 because I don't have that marked yet. So I can just look at the angle 0. Oh hey, that's the same as my angle 2 pi, so I can go ahead and fill that in as a point, an x-intercept. Just one quick thing about the unit circle that I actually had intended to mention earlier and I forgot. The sign of your sine SIGN of your sine, cosine, and tangent functions is determined by your quadrant. So if I write A, S, T, C, so the A is for all, this is for sine, this is for tangent, and this is for cosine. This is the only one of these three that's positive. So here all three are positive, here only sine is positive, here only tangent is positive, and here only cosine is positive. The others are negative in those quadrants. So the way to remember this is to say all students take calculus. And that'll help you keep the signs, SIGNs, straight for your sine, cosine, and tangent functions. Now to fill in the general shape of our graph, I'm going to look at what happens. I'm going to start at 0 and then work my way across to the right. So if I start at 0 and I work my way towards pi over 2, my tangent function gets really close to becoming 1 over 0. And remember, on our limits page, we kind of talked about 1 over 0 means we're going off to either positive or negative infinity, and that depends on the sign of our inputs. So our inputs are all positive here because our sine function is positive in the first quadrant and our cosine function is positive in the first quadrant. So as we get close to pi over 2, our tangent function then gets close to positive infinity. So it goes up forever. Now, similarly, if we had come at it from the other direction, our tangent would have been negative because quadrant 2 here is where tangent is negative, and it would have been going towards an infinity, and if it's negative and going towards infinity, it must be going towards negative infinity. So I drew my arrow going this way because it's at pi over 2 where we have the infinities happening. So here we have a positive infinity and here we have a negative infinity. So that, remember, I got from going this direction towards my pi over 2. Now I'm going to start at pi and continue on to 3 pi over 2. So I'm going to be moving down like this. So here my tangent is positive because I'm in the third quadrant, and it's going to infinity. If it's positive and going towards infinity, it must be going towards positive infinity. And then it's a periodic function, so I can go ahead and fill in the rest of this graph. Just like so. So this is a graph of our tangent function, and I've just constructed it using all the information that we've got from our unit circle, our sine function, and our cosine function. Our tangent function was sine over cosine. We also have another ratio, it's cosine over sine, and that one is called cotangent. Using the same logic as before, I know that my cotangent function is going to be negative wherever, or 0, sorry, wherever my cosine is 0, and that happens at pi over 2 and 3 pi over 2. I also know that my asymptotes are going to happen whenever my sine function equals 0, so that happens at pi and 2 pi. And then I can look at my unit circle and say my cotangent is going to be positive wherever my tangent function is positive. So that means it's going to be positive here, here, and then negative here and here. Moving from 0 to 2 pi, my function is positive, and then from 2 pi to pi, it's negative. So it's going to be positive here, and it has to pass through this point, and then it's negative here. And then moving on around my circle, I have, from pi to 3 pi over 2, it starts out positive, and then from 3 pi over 2 to 2 pi, it becomes negative. So I do the same general shape. Just like so. And this is the graph of our cotangent function. We constructed it using the same logic that we did for the tangent function. I want to quickly define two more functions. So we have secant of theta, and that is designed to be 1 over cosine of theta. Sorry, I meant defined, not designed. And then we have cosecant, and that is defined, did it again, oh my goodness, to be sine over theta, or 1 over sine theta. So, just to say that clearly one time, secant of theta equals 1 over cosine of theta, and cosecant of theta equals 1 over sine theta. And once again, we can use our knowledge of those limits that we talked about and our unit circles to determine the graphs for our secant and cosecant functions. Now, I'm actually just going to use my graph of cosine of theta, because remember, we can construct that straight from the unit circle, and right now the only information we need is the information from our cosine graph. We're not worried about what's happening with the sines while we're graphing the secant function, because the secant function is only dependent on cosine. Now, at theta equals 0, our cosine function is 1. 1 over 1 simply equals 1. Therefore, at theta equals 0, our secant has to be 1. Now I want to take a look at pi over 2. At pi over 2, our cosine is 0, so that means our secant is undefined, so we must have an asymptote. At pi, cosine is negative 1. 1 over negative 1 is negative 1. So I'm going to plot this point here. At 3 pi over 2, we have another asymptote because cosine equals 0 there. And then at pi over 2, our cosine equals 1, so our secant once again equals 1. Now, in order to determine what's happening with the rest of our graph, I'm just going to use the fact that I know 1 over cosine could never possibly equal 0, because there's no way I can plug in a number and get 0 if I have 1 over x. The only thing that might even make sense intuitively would be to plug in 0, but that's not allowed because we can't divide by 0. So that means that our secant function is not going to have any x-intercepts. So that means we're never going to be able to cross the axis. So we're going to approach our asymptotes by going away from the x-axis. So our secant function is never going to curve towards the x-axis. It's always going to curve away from the x-axis because we can never get close to the x-axis because there's nothing we could plug in for x to make that happen. Another way of thinking about it is to say from 0 to pi over 2, my cosine function is positive. So 1 over a positive thing has to be positive. And then from pi over 2 all the way to 3 pi over 2, my cosine is negative. 1 over a negative has to be negative. So these are all going to stay down here and be negative. So you can think of it that way as well. Now I'm going to follow similar logic to construct the cosecant graph out of the sine graph. So the first thing I'm going to do is say everywhere my sine equals 0, I'm going to have an asymptote because I can't divide by 0. So that happens at theta equals 0. It happens at theta equals pi. And it happens at theta equals 2 pi. Now I'm just going to look at pi over 2. At pi over 2, my sine is 1. 1 over 1 is 1. So I'm going to plot a point here at 1. And then here, at 3 pi over 2, my sine is negative 1. 1 over negative 1 is simply negative 1. And just like with our secant graph, we're not ever going to have any intercepts. So I'm going to approach my asymptotes in a direction that's going away from the x-axis because I can't cross it. And because it's periodic, we're going to have that happening forever and ever. This pattern is just going to repeat. So just a quick recap. The period of our sine function is 2 pi. And that means that the period of our cosecant function also has to be 2 pi. Because whenever our inputs and outputs, so whenever our sine function repeats, this repeats. So that causes this to also repeat. So my period for cosine is 2 pi, and my period for secant is also 2 pi. And then my period for my tangent function, remember, was pi, so the period for my cotangent was also pi. As far as the sign SIGN of our functions go, wherever our sine is positive, our cosecant has to be positive. If our cosine is positive, our secant also has to be positive. So they have to be positive together or they have to be negative together. And then also the same has to be true of our tangent function. So perhaps it would be more appropriate to say that they have the same sign over a given interval.